part of the this nice institute that you have in Leuven, and to present my research. So today I will present mostly 15 years of research in the field of exoplanet imaging and exoxodiacal disk detection. And I will present what we plan to do in Leuven with my RC grant in the next 5 years. So the title is the New Paradigm for Exoplanet Detection by Interferometry. So it's quite new. The first detection of an exoplanet by interferometry has been achieved last year, and I will come to that. So it was a big year. So before I jump into the details of interferometry and the science, I like to start with this big picture, long-term science goal of exoplanet science, and which is also my long-term science goal, which is to detect on Earth-like exoplanets and perform the spectroscopic characterization of this planet. And I like this picture of the Earth and the Moon taken by the Cassini spacecraft. So it's a picture you can see, bottom right, you can see the Earth and the Moon. It's a picture taken from 1.5 billion kilometers away from us. This picture here is roughly 600,000 kilometers across. It's in orbit of Saturn, and you can see how tiny the planet is, this pale blue dot that you can see on the right with the Moon. And we want to take this kind of images for planets which are much further away than that. And we want to make a spectrum of these exoplanets. And why do we want to do that? It's because this spectra is really, they are the signature about the nature of these exoplanets. So if you take, for instance, the solar system, some solar system bodies, so the Moon, Venus, the Earth, and Mars, you can see the infrared spectra are quite different. From the Moon, where there are no spectral features, saying that there are probably no atmosphere, to the Earth, where you can see really interesting molecules. And we know if we want to detect signs of biological activity on Earth-like planets, we have a rough idea about how to do that. We want to make a really high signal-to-noise ratio spectrum of the planet and detect specific combination of molecules. And this has actually been done on Earth itself. So this is, you can see the top left here, the optical spectrum obtained by the OSIRIS-REx mission. So it was 2 years ago, 3 years ago. You can see the spectrum as a function of wavelengths in the optical, where you can detect on the planet water and mostly oxygen. And this is really taken on a small patch of the planet. You can see there is a small yellow circle here. So that's from the optical wavelengths. And then from the infrared wavelengths, that's the bottom right plot. You can see the intensity as a function of wavelengths. Also, the different colors here are for different yellow circles on the planet. And you can see a lot of interesting molecules, the methane, ozone, carbon dioxide, and water on the surface. And you can also probe the surface temperature of the planet looking at some atmospheric windows, like here between 8 and 9 micron, or 10 and 14. You can actually probe the surface temperature of the planet and investigate whether this is a temperature which is okay with liquid water and habitability. So we can make this kind of measurement for planet Earth, and one of the long-term goals of exoplanet science today is to obtain this kind of nice spectra on a lot of rocky exoplanets. This is obviously a really challenging task for many reasons. The first one is the contrast. There is a huge contrast between the star and the planet. So on this plot here, you can see the spectrum of the Sun-like star compared to the planet of the solar system. The planet Earth is in blue. So you can see the contrast that we need to reach is 10 to the 7 in the infrared. And it's much more difficult in the visible, it's 10 to the 10. So it's really a big challenge for instruments. On top of that, if you want to observe from the ground, let's say in the infrared where the contrast is better, an Earth-like planet, which would be 10 parsecs away, would be 1 billion times fainter than the thermal background of the atmosphere. So this is also something to consider for your instrument. The second main challenge is angular resolution. It's how well you can distinguish the star from the planet. And I like to show this plot on the right here, which shows the angular resolution for different class of telescope and wavelength. And if you want to resolve, so this is here, this red line, if you want to resolve a Earth system at 50 parsecs in the infrared, where we are really interested in the molecules there, you need telescope which are, I would say, 10 to 100 meters, even more if you go to the far infrared in size. So DLT with this 40-meter diameter can resolve the habitable zone probably of nearby a few nearby stars. But if you really want to do a large number of systems and have statistics and increase your chances to detect a really good candidate, you need really larger telescopes. So you can see this challenge a bit like this cartoon here. It's the analogy that we usually use about detecting a firefly around lighthouse, and you are here at home in Europe, and you are looking at a lighthouse in New York, for instance. It's roughly the same spatial scale, and the contrast is also an issue. You don't see the firefly when the star is really bright next to it. And the other difficulty when you observe nearby solar system is the exosodiacal dust, which can mask your habitable planets. And we know from the solar system that actually the zodiacal dust in the solar system is the brightest component of the solar system. After the sun itself, it's at all wavelengths, this is the brightest component. So quick review about exoplanet science. What we know today, we know that there are a lot of exoplanets and they show really huge diversity. This is plot showing the semi-major axis as a function of planet radius for known exoplanets. And the color shows the equilibrium temperature of the planet. So up to now, we have detected more than 4,000 exoplanets, and they show a huge diversity, but we don't know much about them. We know for some of them the mass, some of them we know the radius, but we don't have a clue about the chemical composition for most of these exoplanets. Over the last few years, we had a better understanding about the occurrence of small rocky-like worlds like the Earth. So this is a plot from the Kepler Space Telescope here showing detection of planets as a function of equilibrium temperature and radius. And you can see if you look at the zoom in the small box, you can see that we detect a lot of we have detected with the Kepler Space Telescope a lot of rocky exoplanets which are at the right distance from their stars to have an equilibrium temperature compatible with water. Here again, we know that they are there. We don't know anything else about their nature. Also, a nice result from exoplanet science over the last few years. We start to better understand the different categories of exoplanets. This is a plot showing the radius as a function of mass. And we start to see different regimes in this exoplanet family. So we have the small world, rocky world on the left, and then we go to Neptunian world with a different slope, so between the radius and the mass. Jovian world, a stellar world. So really having a lot of data and observing a lot of exoplanets is required to build this kind of knowledge. And this is the same for atmospheric properties. We need instruments to characterize a lot of exoplanets. So the big questions today, as I said, the big question today in exoplanet science is what is the chemical composition of exoplanets and how they compare to what we have in the solar system. And the other big question is how do the exoplanets form and evolve? So there are a few scenarios to explain the formation of exoplanets, but still poorly understood. So in order to characterize the chemical composition of exoplanets, there are two different techniques that I will show on this plot here, mass versus period. There is a transit technique, which is really good at detecting planets which are close to the star, and from our perspective, which are aligned. The orbital plane is aligned with us. And so you can do transit spectroscopy or secondary eclipse spectroscopy by looking at the light from the star transmitted through the atmosphere of the planet. But using this method is difficult to characterize Earth-like exoplanet around a Sun-like star, because you have to wait 1 year for a transit, and it's difficult to build up the signal-to-noise ratio that you need. The other, first, so yeah, you probably all know that. How does it work? So you measure the flux deficit as the planet passes in front of the star. And there are 3 projects that will do that for small planets like Ariel and James Webb Space Telescope, in which we are working in Leuven involved. And the other technique is direct imaging. This is my expertise, my field of expertise, where we angularly separate the flux from the star from the flux from the planet. And it's really challenging to do that. And as you can see, this method is really good for planets which are on wide orbit. I will come back to that later. And we have only a few planets detected like this. Approximately 10 to 15. In order to do that, in order to do a direct imaging, as I said, you need to reach really high contrast between the star and the planet. And there are a few techniques to do that, and mainly 2 that I've been using that widely used in the community. The first one is coronagraphy, and the second one interferometry. And up till last year, only coronagraphy was successful in imaging exoplanets. I like this comparison to Star Wars, because interferometry is it's much more difficult to master than coronagraphy, because you have to work with different telescopes and co-phase the telescope between them. But if you can master the technique of interferometry, you can actually get really better results than with coronagraphy, and I will show you why later. A short movie showing how does it work for coronagraphy, direct imaging. So with a single dish telescope here, I'm not talking about interferometry yet. So you have the light emitted from a distant star going through the telescope, and then first going through the atmosphere, and you see the turbulence of the atmosphere directly on your detector, and then use a wavefront control system in real time in order to correct the mirror. Then you can stabilize your PSF. And then the next step is to mask the light from the star. And when you do that, you can improve the contrast of your observations and look for planets in the spectral field on the background field. So that's the first step. That's one of the first pillar of direct imaging. So you need adaptive optics to correct for the atmospheric turbulence. And the second step, you need some kind of method to distinguish the planet from spectral noise, from your telescope. And the way we do that usually is the basic way is angular differential imaging, where we use the fact that the pupil of the telescope is stable during the night. And so the telescope is here. And then when you follow the star across the sky, you can see the field around the star, which rotates. And you can use the rotation of the field compared to the fixed pupil to extract the planet in your data. I will show you how. So this is here a sequence that I will start. It's background subtracted images obtained with the LBTI, so a single dish imaging telescope. You can see the star is really bright at the center here, and there are 4 planets in this sequence that you can actually see, at least 3 of them, and you will see them move. So there is one here moving slowly. So when the movie is slow, it's difficult to see them. There is another one here. So you see the PSF is stable because your pupil is stable, but then the field rotates, and then you can see the planet. And if I go faster here on the movie, you can better see the planets. So that's one step without a coronagraph here. The next step, you can subtract your starlight. In this case, it was not done with the coronagraph, it was done in post-processing. This is the same movie with PSF subtraction, and you can see to better see the planets now. There is also another one here. And there is also a fourth one here that you will see better if I move faster. So if I move really fast, it's easier to see the planets. So this is a sequence of frames during a given night. And so the second pillar of direct imaging is really to process the data, and this is what you get in the end when you do the data processing properly. You can see the 4 different planets. And there are different instruments doing that. So single dish instrument, GPI sphere at ESO and Paranal. This is actually a short movie showing, this time it's not the motion during a night, this is actually the orbital motion over the years. So several images that you can see. And there are different instruments doing that, and also DLT has also imaging modes that will be able to look really much closer to the star because of the higher angular resolution. A few examples of directly imaged exoplanets. I won't, just for illustration, I will not comment on that. They are mostly giant Jupiter-like exoplanets. This is the current status about exoplanet imaging. So we know more or less 10 planetary mass companions which are on close orbit, so less than 100 AU. Another 10 planetary mass companions on wide orbit, so more than 100 AU. And we have also observed roughly 30 objects which are near the deuterium burning limits, or more or less 13 to 20 Jupiter masses. And this is a true state-of-the-art survey of planet imaging. I can take the GPI on the right here. You have the Jupiter mass, and you have the semi-major axis. And so current imaging telescopes are really good to detect, I would say, Jupiter down to a few Jupiter masses, exoplanets, beyond the snow line. So beyond a few AU, I would say from 5 to 100 AU. That's the current parameter space. And why is that? So the main limitation is the contrast. And the second limitation is, as I explained before, the angular resolution. And so for at least the angular resolution, there is a known solution to beat the angular resolution of your telescope is to do interferometry. And in principle, with interferometry, you can synthesize a telescope which has an equivalent size of the baseline, so the distance between the two telescopes. So in the case of the VLTI that you can see here, you can in principle get the angular resolution of a 200-meter telescope near Earth. There are different instruments on the VLTI. The baseline goes up to 200 meters. The instruments cover different wavelengths, Pioneer, H-band, Gravity, K-band, and low to high spectral resolution. Matisse also came online last year, so L and band. And last year, the first detection and characterization of an exoplanet was reported by interferometry. This is what you can see on this image here. So this is a picture of HI 799 with the 4 planets. This is the system as I showed before. And the gravity team characterized the spectrum very well, actually, the spectrum of the inner planet here. So this is, you can see the K-band spectrum on the plot here. And the way they do that is they put one fiber of the gravity instrument on the star for fringe tracking and to co-phase the instrument. And they put the second fiber on the planet. So you have to know in this, the way it works with gravity, you have to know where your planet is and put the fiber on it. And why it's a new paradigm, it's because when you do interferometry on an exoplanet, you have a way to distinguish speckle noise from the planet flux using the coherence of the light. Only the planet flux will be coherent, while the stellar flux won't be coherent. So you can, using interferometry, you can, at least for this example here of gravity observation of this planet, they achieve SNR, which is 5 times more precise than with direct single dish telescopes. And they also achieve an extreme astrometric precision of 14 microarcsecond, also because they use the long baseline of the VLTI to reach a high angular resolution and astrometric precision. And they are actually working now on the gravity plus upgrade to go down to 10 microarcsecond, even better. That was for last year. And this year, actually a few months ago, they also published the first direct observation of an RV discovered exoplanet. So this is also very important because this is the first time we have different constraint, different way to obtain the mass of a planet. We have the mass from the radial velocity, and now we can have a constraint also from the direct imaging. This is the first time a planet which has been discovered by radial velocity has been detected directly. This is beta peak C in this case, which has not been seen by instrument like SPHERE with single dish instrument. Only with interferometric combiner it was possible to extract the planet signal where it was supposed to be from the radial velocity predictions. This one is much fainter than the other one, so the SNR here is not as good, but they detected clearly the planet at the position that was predicted from radial velocity. And they were able to extract some information about the planet temperature mostly. So this is using the gravity instrument on the VLTI. I think I will skip that because I'm running out of time and I have a lot of other slides. So how does it work? You can also use gravity to search for exoplanets. So it's not ideal because you have to scan. So this is what they've tried to do with the EUMIC system. EUMIC is a next-gen bright debris disk. And there are various clues about the presence of an exoplanet. And so they put the second fiber of the gravity instrument in a different position, looking for the planet. And by doing so, they also managed to construct some kind of contrast curve. So here, these curves give you the contrast you can achieve as a function of angular separation with the gravity instrument. And so the planet I've shown before, they are all roughly in this region here, around 10 to the minus 4 to 10 to the minus 5 contrast. So these are the two techniques to characterize exoplanets, short period planets and long period planets with direct imaging and transit. And all these planets here are discovered by radial velocity. We have the first one that has been characterized by interferometry, directly characterized this year. But we want to do more. We know that most of exoplanets are here. This is the most interesting region because this is where the habitable zone is for most nearby systems. And this is also within the snow line of most nearby exoplanet systems. So if we want to characterize these exoplanets, which are there, we know that they are there, we need a better angular resolution in contrast. So if I go back to this picture here of the same system, we want to probe the region which is really on the star here with interferometry. This is where the habitable zone here. And this is also where the peak of exoplanet distribution is located. This is a graph illustrating that. So you can see the occurrence rate of exoplanets as a function of orbital period. This is a recent paper here. And you can see the snow line over here. So this is where we are today with single dish 8-meter class telescope. We have a detection rate of roughly 1%, even less than that. With the ELT, we'll go much closer to the snow line. We will be over here. And then if you use the long baseline of the VLTI and the high angular resolution, you can really go into the snow line for nearby planet forming region where most exoplanets are. The challenge is now to reach the contrast that you need with the VLTI to detect and characterize these exoplanets. This is another plot showing that the measurement, this is actually I didn't say that, but this is RV measurements here. This is also confirmed by planet formation models and migration models. You can see here prediction of the planet formation models, mass and separation, physical separation. And most planets are located within the snow line for the rocky and gas planet. So what is missing to do that? We need high contrast and we need the VLTI. So the VLTI is probably the most advanced interferometric facility in the world with long baselines and really stable infrastructure, always improving. And then over the past 10 to 15 years, there have been a lot of progress in high contrast interferometry in the US. And so I have a project now to combine the strengths of the VLTI, which are the long baseline and really stable infrastructure, with the techniques that were developed in the US over the past 15 to 20 years, and especially nulling interferometry. So this is the pitch for my ERC grant. So this is a new project starting last month, and we will build a dedicated nulling instrument, so a high contrast interferometric combiner for the VLTI, leveraging a lot of progress in the US with the Keck-Nuller LBTI and also new technique to calibrate the instrument that are being developed in the community, like kernel nulling. So Romain Logier will have a talk about that in a seminar about that in 2 weeks. Kernel nulling, it's a way to combine the beams to achieve really high contrast. So the project is funded by the ERC and Opticon, and we have partners different places in Australia, Arizona, ISO, IPAG, Cologne, Liège, also NASA, working on different parts of the project. So this is an instrument that will use nulling interferometry. So far, there has not been any nulling interferometric instrument on the VLTI. And so nulling interferometry is a way to remove the starlight from the signal that you want to measure. And we have demonstrated that we can achieve the contrast that we need on the instrument in the US. And how does it work? Basically, you combine the light from you have two mirrors. You combine the light of the two mirrors in phase position. When you do that, you can remove the starlight. At least you remove the light which is on axis, which is an exact pi phase between the two beams. And when you observe with an instrument in this way, you produce some kind of transmission map. This is a transmission map that you use in nulling interferometry, which is some kind of photon sieve that you put on the sky. Every brightness distribution that falls on the dark stripe will be removed, and anything like a planet which falls on a white stripe will be transmitted to the output of your instrument. This is an example of measurement taken with the LBTI. So you can see the flux of the overlap stars. So you can see at the top right here, the two beams from each telescope are overlapped. And we are scanning the phase to get the pi phase exactly between the two beams. And at some point, we find the pi phase shift and we stabilize it with a fringe tracker. And we can remove the starlight from the detector, and then you can barely see now the planet, the star. So you can barely see the star, which is removed by nulling interferometry. So what will be the science case of a VLTI instrument which achieves such high contrast? The main science case is to detect young and forming exoplanets in nearby planet formation regions. And what you can see here are predictions from planet formation models, BT settled models in this case. You can see the contrast at L band as a function of H and wavelengths for different planet masses. And if we can reach a contrast of 10 to the -4, we can detect planets which are, I would say, for instance, 5 Jupiter masses up to 50 million years. This is for the big classical model. This is for cold start model here in blue. And really, the L and M band are the sweet spots to detect exoplanets. This is the same models here as a function of wavelengths. L and M band are here, 3.8 and 4.5. This is where the contrast is easier than at shorter wavelengths at K band, like gravity. Like gravity is here. So this is one of the main reasons we choose the L band, is because the contrast, which is really the main issue in nulling interferometry, is easier here. We can make prediction about what kind of science here we would get if we look at planet forming region at 130 parsecs, for instance. So this is the probability of detection in percent as a function of time since disk dissipation. And you can see that really I5, which is the name of the instrument here, is the best machine to have a high probability, in higher probability of detection than even with METIS, so the 40, the infrared instrument on the ELT. And the main reason is not contrast here, it's really the angular resolution. You need the VLTI baseline to go and look for these planets which are within the snow line. You can also look at known exoplanets. So this is the plot showing the contrast at L band for known exoplanets. And you can see the angular resolution of an 8-meter class telescope here, the angular resolution of the ELT, and the angular resolution here of the VLTI. So really to go in this region, you need the VLTI. So this is where we are right now. This is the 1% of exoplanets that we know, more or less, with coronagraphy. If you suppose that you have the same performance on the ELT, this is where we would get with non-aperture masking coronagraphy. This is what we can do with gravity today. This is what we can do on axis with gravity and Pioneer today. This is the parameter space of nulling today, and mostly because the nulling instrument on the US instrument don't have a long baseline, and this is what we want to achieve with this instrument. So to do nulling with the VLTI, and for that we need a really good precision on the starlight suppression. Other science case. Also, there is a big science case on exoxodiacal dust. So there is a lot of activities in this field because the exoxodiacal dust is actually, it's both interesting for evolution of planetary systems, but also it's a noise source for future direct imaging instruments. And so on the US side, NASA has put a lot of money in nulling instrument to detect this exoxodiacal dust. This is illustrated here because later, if you want with your LUVOIR or ABEX instrument in space, you look at a planetary system and you have a lot of dust in the planetary system. You won't see the rocky exoplanets, and you need to know in advance which system has a lot of dust and remove it from your target list. And this is why the LBTI was funded, the Keckner. And so this is here, for instance, the result of the LBTI. This is the ZODI sensitivity. 1 ZODI is equivalent to the brightness of the solar zodiacal cloud. And this is also a good plot to showcase the performance of nulling instrument. This is the precision of WISE, so a space photometric instrument, just measuring the photometry of the star. The typical precision is 1000 ZODI. With the Keckner first generation nulling instrument, we went down, we gained more or less a factor of 10. And then with the state-of-the-art nulling instrument, we gain another factor of 10 in precision. But these instruments are in the north, so they only characterize the targets in the northern hemisphere. And we want an instrument to do the same kind of study in the south for the south targets. There is also a science case for binary across the HR diagram and detection of faint binaries, high contrast, so especially binaries around high mass stars, which are really bright. If you need a high contrast, this is the instrument you would need, high contrast and high angular resolution. There is also the long-term science goal that I presented earlier in my first slide. So this instrument won't go into space and it won't do rocky exoplanets, but it has the same working principle and observing mode and as the LIFE project. This is a project that was submitted to ESA last year for the future L-class mission. And the goal of LIFE, the ambition is to do a lot of terrestrial exoplanets, constrain the habitability, the biosignatures on rocky exoplanets. And for that, you need to go to space. You need the sensitivity that you have in space with a nulling instrument in space. And with the VLTI on the ground, we will prepare the data acquisition and processing technique for LIFE on the ground. So there will be mostly the giant exoplanets, young giant exoplanets, which we can do from the ground. We do precision spectroscopy and astrometry with the VLTI. So this is for the long-term science goal. So we are waiting for the reply from ESA about the selection process. Probably in January, we'll know whether the LIFE science case was selected for a future class mission. We'll skip that. We have, in December, we have the kickoff meeting for the SCIFY ERC MyERC project. It's an online meeting, December 3rd and 2nd and 3rd. If you're interested, you can register by looking at the QR code here. And then 2 days before that, the same week, we'll have LIFE Workshop 3 to discuss about the LIFE project. So a lot of colleagues are involved in both projects. So we have a full week dedicated to nulling interferometry, both long-term and shorter term. Before I finish, I would like to mention that I'm in charge of the VLTI Expertise Center. I'm moving now to Leuven. And so this can be useful if you have ideas about using the VLTI for your science. We are here to help you with observing proposals, preparation of all data reduction. So there are a network of 6 different VLTI expertise centers in Europe, a bit like what we have for ALMA. And so this is the node for the Belgium and Netherlands is now in Leuven. So if you have ideas or if you don't know how to reuse your data, you can contact me and we can help you. We have resources for that. We will also co-organize with ESO the VLTI Community Days in 2023 in Leuven. So I will keep you informed. And the idea also is to exchange information and experience between the VLTI and ALMA expertise centers, which are really useful. The VLTI expertise centers are not well known yet. So takeaway messages of my talk. So there is a new era of exoplanet characterization with long baseline interferometry, just starting the first detection last year. And then I have an ERC project to keep going. We need the VLTI baseline for really exciting science, exoplanet science, mainly to the angular resolution, so accessing the snow line. So the project is just starting. So if you're interested, you can contact me about anything in the science or being involved. Same for the VLTI Expertise Center. When we have call for proposals, we can exchange ideas and put our tools in common if necessary. And that's all I have. Thank you for your attention. Let me know if you have any questions.
Thank you, Denis. That was very nice, actually. So if anyone has a question, please say so in the chat and I will call your name. I try to give priority to the younger people, but of course, the more senior one will also have an opportunity. Anyone, any question? Yes, please, Cyprien.
Yes, so thanks, Denis, for your presentation. I was wondering if the two telescopes have a different flux is that a problem for the nulling? Is that an effect? And how do you deal with it if there is an effect?
Yeah, it's obviously a problem, but we are quite insensitive to that in some sense, because from the ground, you are mostly limited by the thermal background from the atmosphere. So you can tolerate quite a bit of intensity mismatch between the two beams. But that's true, the intensity mismatch will limit your null depth. So it will limit how well you can subtract the starlight optically. But we can calibrate that quite well in post-processing. So this is not a big issue as long as it remains below a few percent. We can achieve really high contrast, let's say 10 to the -4, even if your raw null depth is only 1% due to this intensity mismatch. A lot of that will be taken care in post-processing.
Okay, thanks.
Okay, and then I will move on to Denis.
Yes, hi. Thank you for your presentation. I was wondering if there were some kind of limitations linked to the hardware that is being used, i.e. detectors or optical components giving some, let's say, maybe some scattered light into the instrument, and whether these things are being looked at and analyzed as well.
Yeah, yeah, there are many components in such an instrument. So the detector is obviously a big part of the instrument, and it will limit the spectral resolution that we can achieve. So basically, you have not a lot of detectors that work at this wavelength. Basically, there is only one that is sufficiently good, which is the Hawaii 2RG, which has a read noise of 15 milliseconds, 15 electrons RMS, sorry. And so this will limit your spectral resolution at some point. Another big component is the integrated optics. So this is a research project, and we still don't know yet exactly how we will build this integrated optic components. What's the best way? We can do the fiber option or the lens option, micro lenses option. And so these are two paths that we are looking at right now. But the best way to manufacture this beam combiner for the L-band. So we are actively working on all these issues. Another big one is the polarization of the VLTI beam train. So we need an active polarization control system. So we are in touch with ESO and with the gravity team to develop the hardware that we need for nulling.
Yeah, thank you.
Sen?
Thanks. I would have a question about I mean, right now you talk mostly about detections. How about obtaining spectra? Is that straightforward with interferometry, or are there additional difficulties which we would face?
So this is how it's done with gravity. You can disperse the light after beam combination. So you combine the beams between the two telescopes, and then you disperse the light, and you can get a spectrum. I think for gravity is the gravity detection is 2000 spectral resolution. So there is no problem to do that. The issue is that the more you disperse your light, the lower your SNR for given integration time. So this is something to consider when you build the instrument. It's the trade-off between spectral resolution and contrast that you can achieve. But in principle, there is no problem to disperse the light after the beam combination and get the spectrum of the planet. This is what we will do. We will follow the same principle as gravity for that.
Okay, then we go to Abigail.
Hi, thanks for a really nice talk. I was wondering whether nulling interferometry would have a significant improvement on our view of disks in the infrared, protoplanetary disks, in terms of finding substructure or looking for disks that are much more embedded than those that can be observed with sphere.
So if your disk is really embedded, I think you will have to rely on regular interferometry. So this is something we haven't discussed yet, but we might have a regular interferometric mode, so without the pi phase shift, in order to enable this kind of science case. Because there is no point in doing nulling interferometry for an object which is where there is no really bright central star. You will just subtract a part of the disk that you want to characterize. And so I think for this kind of sense case, we would need a way to use a regular interferometric mode. And the instrument will be designed for high stability anyway, so you will get a really high contrast if you want to look for structures in your disk. This instrument will do the trick. Yeah, but the highest contrast probably will be achieved with nulling. I mean, that's the point.
Thank you.
Okay, Luca. Luca, you might still be muted.
Can you hear me?
Yes.
Yes.
So I have a question. You show the average equilibrium temperature of planets that we observe, and I noticed that in the graph there are also planets with temperature above 4,000 Kelvin. So I was curious about what kind of planets are those very hot planets.
In one of my plots. Oops, what's going on? Yeah, I think there might be some really hot planets. It's the plot has been computed for equilibrium temperature. So if the planet is really close, it must be a hot Jupiter for which the computation of equilibrium temperature is probably too high. I suppose there are not a lot of planets which have this kind of temperature. Go back. You mean this plot?
No, you show another one earlier in the presentation.
About the temperature of the planet?
Yes, if I remember correctly. This one.
Okay. Oh yeah, this one. This one is directly from the NASA archive. So I'm not sure what's in that, but I guess this is for a planet which is really close to the star. Yeah, the equilibrium temperature is just that high because it's really close, but I'm not sure exactly what's in this computation here.
Okay, I understand. Thank you.
We still have hands.
Yeah, Denis, thanks for the talk. I have a question about the VLTI Expertise Center. Can you tell me a bit more about it? Is that how much, I mean, is that a very considerable amount of work, or is that, because the ALMA regional nodes, they're also responsible for data reduction and data analysis, but the VLTI Expertise Centers are a bit differently organized, no?
Yes, so it depends what you want to do. So far, what we have done with the center in Belgium is help with the proposal, and if there was a lot of work, a lot of reducing work to do, we would get in contact with the center in France, which has a lot of bigger infrastructure than us. So what we can do, it depends really about the availability of the people that we have in the center. Up to now, we were 2, and we were spending 5 to 10% of our time to help with the proposals mainly, and to coordinate the data reduction with colleagues in other centers. But we will have more fundings for that soon, next year, and there will be someone dedicated to the center and to 25%. And so we will, I think what I would like to do is to have a dedicated server in Leuven with the latest version of the pipelines for both Gravity and Matisse, that everyone can use and that is maintained by a single person. That would be one of the tasks of this new person that we will hire next year.
Because we have quite some expertise in VLTI, many of us, so maybe we can also think on how to optimize that in the whole institute, I guess.
Yeah, I've been talking with Jack
yes.
about that. I agree. We should coordinate because I don't know yet everything that is done at the institute, and
yeah.
We will have someone to coordinate that next year. So.
Okay, perfect. Thank you. Yeah, Corona doesn't help in that respect either.
No.
Indeed. Then if we have still David.
Thank you. I'm curious, how good can this interferometry technique get? And so, for example, if there's a planet and it's the size of Jupiter, and let's for simplicity say exactly 1/2 of it is covered in water and the other half of it is perfectly covered in rock, how close would it have to be for the VLTI to not only be able to see its orbit, but to actually see some sort of surface features like half water and half rock?
Yeah, I think for that you need an interferometric facility which has much larger baselines. That's not the baseline that we have on the VLTI is not large enough. I think you need something like 10 or 15 kilometers in baselines.
Okay.
If you want to do that on the nearest planets, I know that there are programs to detect moons around exoplanets with gravity. So you can actually, with the VLTI baseline, resolve the distance between the Earth and the Moon for nearby planetary systems. You can do that with the VLTI baselines, but you cannot distinguish continents yet. You need larger facilities for that.
Thank you.
Any other questions? If not, I just noticed that we are with 60 participants. I think that's a record-breaking number. So Denis, you apparently excellent. So thank you again. And I'm sure if you have any of you have any questions, I'm sure that Denis is willing to answer them through either Slack or email or something.
Yeah, don't hesitate to contact me if you have questions.
Thank you very much again, and then I will hopefully see all of you in our next week seminar at the